All right. Good afternoon, everybody. Welcome to this CPS Week 2025 tutorial on Scenic. Scenic is an open source probabilistic programming system that we've been developing for the past almost 7 years now. I'm Sanjit Seshia. I'm a professor at the University of California, Berkeley. Scenic is a project that started in my group at Berkeley. And now I co-direct this project along with Professor Daniel Fremont at UC Santa Cruz and Dr. Edward Kim, who's a postdoctoral researcher at UC Berkeley, will also be conducting this tutorial with us. And the Scenic project, we're really doing this tutorial on the behalf of a large team. So there's a large set of people who are actively developing and extending and improving Scenic. And we can't list all of their names here on the slide. So it's all listed at that URL over there. Okay, so in this tutorial, it's about 3 hours with the extra half an hour break. So we'll go till 5:30 p.m. So this particular segment that I will do will be an introduction to Scenic. And then we will have a more detailed tutorial on various aspects. All right. The other thing I want to mention is we would like to keep this interactive. So you can interrupt, ask questions at any time. And we will also have some hands-on segments in this tutorial. Okay, so the context for Scenic is that as we are all already well aware, there is widespread use of machine learning and more broadly of AI in all kinds of systems today. But of particular interest to this tutorial are safety-critical autonomous and semi-autonomous cyber-physical systems. Self-driving cars are a good example of that. And I'm sure everybody in this room is well aware of how the self-driving car technology has grown over the years. But at the same time, this technology has not really reached the levels of adoption that people were projecting 10 years ago, right? And one of the biggest obstacles that is widely recognized is a general lack of safety and dependability and robustness of this technology. So if you were looking at the news 10 years ago, there were rosy predictions of self-driving cars being on the road by 2020 and being widespread. And although we've made a lot of progress in this regard, if you recall, 2020 came and went, and that didn't really happen. And those rosy predictions were replaced by reality, and actually a bit of a pessimism as well about the technology. One of the unfortunate side effects of all of this has been that there have been accidents and incidents that involve the use of, potentially the use of AI machine learning based components in these systems. Right. And so we've seen this technology, even as it's progressed, it's really not reached its potential. Now, I think many of us are strong believers that this kind of autonomy is something that can be of great benefit to society, can help lots of people who are not otherwise able to access these kinds of intelligent transportation technologies, be able to be more mobile and have better lives. And so I think it behooves us as engineers and scientists to see what we can do to advance this technology. For a long time, for more than 10 years, in my research group, we have been pursuing what we call the verified AI research agenda. And the idea here is that we want to create a design flow, and I'll explain what I mean by that, for AI-based autonomy. That is AI-based autonomous and semi-autonomous systems that is supported by theory, like you see in this conference in CPS Week, techniques where the theory is implemented in algorithms, and tools where the algorithms are then implemented in software tools that people can use for design that can ensure this kind of safety and dependability and robustness. And what I mean by design flow is that if you go to the different conferences in CPS Week and CPS-IoT Week, you'll see there's lots of nice papers presented, and some of those papers are implemented and they will show results, and maybe some of those tools are available open source. But those tools, many of them don't go beyond the particular paper or the thesis that is involved, that project is all about, right? And what we would really like to do is take all of those techniques that are geared towards improving the safety of AI systems, AI-based CPS, and connect them all together, right? Have them interoperate so that together the community can improve the level of safety. And that really means that we have to think about the overall design problem, right? All the steps in the design cycle as you go from high-level modeling and requirement specification all the way to implementation, monitoring in the field, right? And closing the loop. All the different steps there, develop tools for them and have those tools have the ability to work together. So that's what I mean by a design flow. It's like something which, for example, the chip design industry has today, where there are lots of tools used to the design of computer chips, and they address various problems, and together they raise the level of reliability that we have with these systems. Okay, so we wrote this position paper towards verified AI about 10 years ago, and I encourage you to read more if you are interested in the broader research agenda here. Now, a key component of this research agenda is techniques coming from the area of formal methods. So what is formal methods all about? In this particular area, formal methods is a class of techniques that are rooted in mathematical rigor that you can use for various steps in the design process. So for instance, modeling the world in which the autonomous systems operate, environment modeling, that is a task that formal methods can be applied to. You can apply it to mathematical specification of requirements and metrics, safety metrics. And then you can develop algorithms for verification and testing based on formal methods, and also apply them to other steps in the design flow like synthesis and debugging. And ideally, we want to be able to build these into the design process so that at the end, rather than trying to verify or test something after the fact, you can build safety into it from the beginning, right? And so this has really been the agenda for this project, and it has been supported by many sponsors over the years. All right, so two of the outcomes of this effort are two open source tools, Scenic and Verify, and these are really twin tools, right? So they work together. So let me explain what these are. So Scenic is a high-level probabilistic programming language for modeling the world or the environments in which autonomous and semi-autonomous systems operate. So you can think of Scenic as the front end, the modeling language, the representation. And Verify is the back end. It's a open source toolkit where you can specify requirements, and then you have a suite of algorithms for the various steps in design, verification, testing, and debugging. And as I mentioned at the beginning, these are open source tools. These are projects that we have had online for about 6 years now, I think. And they've been used across various sectors, industry, academia, and government agencies. And what we would really like to do, even through this tutorial, is to grow the community and really connect the different research efforts and tools together so that we can share not just data and tools, but also scenarios and metrics that people can use together to improve safety. Okay, so I think we are very interested in this tutorial. If you are not yet using Scenic and you would like to, we are happy to work with you to help you facilitate that. And if you would like to contribute to Scenic project, or you connect your tools to Scenic and Verify, then we are happy to do that as well. Okay. All right, so here's the outline for the tutorial. In the next 20 minutes, I'll give you a quick overview of Scenic and its applications. And then I'll turn it over to Daniel Fremont, and he will introduce you to the Scenic language, currently in version 3.0. And the idea is that we will, in the next hour before the coffee break, we will introduce you to the various language features, and then there will be a hands-on session where you can try it for yourself. Then we'll have a coffee break, and then at 4 o'clock, we will restart, and we'll talk mainly about applications of Scenic. One set of applications to verification, testing, and debugging of the different components and the systems in the autonomy stack, and another set of topics on how you can use Scenic for data generation. And then we will conclude and we'll talk about some of the future directions that are going into other areas of CPS overlapping with other topics, including generative AI, extended reality, and so on.